Hello, welcome. So in this series, we've been building a data-oriented C compiler in C. And in the previous episode, we got the beginnings of a parser working. There were a few comments on the previous video, and one of the comments was, why don't you use a library for dynamic arrays and hash tables and things like that? And that's a good point. So you might see there's SDB-DS here by Sean Barrett. And I decided to add this in here. I don't think I'm going to convert existing code. I'm just going to start using this going forward. I might refactor code later to use this library. It does have some documentation here. And the main reason why I didn't want to use this sort of code is that I was afraid it might make it more difficult to understand. But actually, there's really good documentation for this library. It kind of lists what all of the different functions do. And it's pretty concise. So there's a few lists in this documentation. So if you're not sure what one of these functions does, I would recommend just having this open and referring to it as you watch the video or while you're looking through the code or whatever you prefer to do. Everything is up on GitHub. In my GitHub repo, there's a link in the description both to this page where you can get the latest version, because the latest version is not here. This version is 0.1 and there's 0.67 available here. And I'll also link the GitHub repo where you can find the source code for each episode of this series. So I think I'm going to start using this going forward. It'll save me the time of implementing a hash table. And, to be honest, you can find out how to implement hash tables quite easily. There's probably thousands of videos on that on YouTube, and most of them, well, a good chunk of them are in C. So that should not be a problem. And the nice thing about this is there is these dynamic arrays, and they have a really nice syntax. So yeah, I think I'm going to start using that. Array insert, for example, would have been really handy because in the last episode, I did a memory move, and this would have avoided having to do that. So yeah, I might convert that code because I'm not 100% sure I did that properly. And I presume this one's been tested way more than my code has. So what else? So I did some thinking about what to do in this episode, and I'm just going to kind of use this as a scratch pad here. So a regular compiler kind of looks like this. Well, the compiler I plan to build looks like this. So we've got... So what I plan to build is this pipeline. You've got the tokenizer that produces tokens, which go into the parser. The parser produces an abstract syntax tree. Oh, I'm missing type checking. I'll just call it semantic analysis. And apparently I can't spell. There we go. I'll just do some abbreviations. So that's kind of what I plan on doing, is tokenizer to parser, which produces an AST, to semantic analysis, which produces types, or basically labels the abstract syntax tree with types, and also looks up symbols. So you get a symbol table out of this. And then we convert it into IR, which is intermediate representation. And then the IR gets converted into IR again, but at the machine code level. And then register allocation happens, which is the single best optimization you could implement if you only implement one. And I'm not sure, but I'm thinking I might just implement register. Well, there's a few other optimizations that are pretty low hanging fruit that we can do. And then from register allocation, we go into assembly. And I'm not going to go all the way down into machine code, but, well, actually, I kind of am. I have an idea for how to embed custom ASM within this compiler so that it can go all the way down into machine code, which will be nice. So that's kind of the plan. Now, I have a dilemma. What I could do this at first. So it basically just goes from the parser directly into assembly. I kind of have that sort of implemented in gauzy.c currently, because this is directly producing assembly. The issue I have with this is that I'm going to end up basically throwing out that code almost immediately and then going towards this. So I've kind of made the decision to stay at the current syntax. So just adding and subtracting numbers and build the entire pipeline all the way to the end before adding more features. There's pros and cons to that. Technically, I'm not doing incremental building of this compiler anymore if I do this, because usually what you would do when you're incrementally building is you would only build out these things as you need them. So you would add syntax features until you end up needing one of these other constructs, and then you build it at that time. Yeah, some of these I can do that for, because right now the only types in the entire program are integers. So I could skip semantic analysis for now until there's more than one type. I can also pretty much skip register allocation for now. And in fact, I could probably skip IR for now and just go straight to machine code IR. So yeah, I'm kind of thinking maybe something along the lines of this for now, which with kind of a stub register allocator, kind of like this. So then we do need an IR. And so that's what we would build next, but we can skip semantic analysis for now until we have more than one type. And we can skip just a regular generic IR for now, and just go straight to the machine code version. And then it would go through basically a super hacky register allocator that's not going to do a proper job, but right now we don't have enough syntax to really exercise a proper register allocator. And then go into assembly from that point. So I think this is the plan going forward. The nice thing about doing this is viewership for long series tends to go down as the episodes come, because more and more people get discouraged that, oh, there's 25 episodes before this one. I don't have time to watch 25 episodes, so I'm not going to watch the series at all. So if I get to the interesting stuff, which is, in my personal opinion, in this area here, well, really, all of this is interesting, then at least I'm doing so earlier in the series, and it's less likely that people will drop off, and hopefully then will be more useful to people. So I think I'm going to do this. Yeah, let me know in the comments if you really disagree, but I think this would be more interesting than just trying to do it kind of the traditional way. Mainly because that's been done before. If you want to see the traditional way of incrementally building a compiler, just go through the chibicc commits from the beginning all the way to the end. It's really well documented how he did that. But yeah, I kind of just want to get on with things. So let's just get on with things. Let's just undo here. All right. So what's next? Let's see. let's kind of use this as a sketch pad again for the IR section of things. What do we need to build an intermediate representation? Well, the IR is basically abstract instructions. And an instruction has an operation that it does. So we could have an enum for an op. So these would be the opcodes that we're currently using. A way of loading an integer into a register, basically adding to a register and returning the result, subtracting, and we've got this error opcode that I'm using to set the error level of the process when it exits. This corresponds with the instructions that we have in here that we're using. So we've got, this is basically load immediate, which is just a move of an immediate into a register. And actually, we're kind of mirroring this in that we've got a token for int, and we've also got a way to represent that in the abstract syntax tree as well as the IR. And the same for add and subtract, and EOF I'm just calling error because it generates the error instruction. So one thing that's really handy is to have an op definition. So that can have like a name, and also there's going to be other things that we can store in here. One thing that might be nice to have in here is whether or not the operation has whether or not it's like a constant or not. Maybe, I don't know. I'm not too sure what we need in here, but let's go with this for now. So then we can have the input type on here. Well, we can do the op defs. Yeah. I think actually what we're going to do is inputs will take an operand. They only take one operand. Let's rename this to, actually, let's rearrange this because this is going to make a little bit more sense. And I actually want error to be 1. And my auto formatter does this. I don't really like it, but that's fine. Whatever. Once we add more information to opdef, it'll sort itself out. So yeah, invalid opcodes, generally we wouldn't do that. That would indicate some sort of error. Add has 2 operands, so 2 inputs. Error has 1 input, and that would be the result to set the error level to. And then we've got, that's the same as add. It has 2 inputs. And then we've got an int that has just an integer constant in it. So then we would have okay, so this is the idea then. So we would have an instruction. Now I could call this node, but then I'd have to rename the AST nodes to AST nodes. Yeah, this name may not make sense after a little while, but let's go with it for now. So we've got this. So what I'll do is bitpack this later, where I can probably bitpack these two together fairly easily, but I'm not 100% sure what'll go in this structure, so it'll be easier to bitpack it a little later when it's more fleshed out. So for now, this isn't as small as it could be, but it'll be good enough. And then we've got a union in here that unions the integer constant, because constants don't have any inputs. So yeah, it just makes that easier. And then we've got also the two inputs, 1 or 2, and then you would check the input type on the opdef to know whether there's like how many inputs there are, or whether this is even valid at all for that opcode. Another thing that we can do later, some instructions take more than 2 inputs, but we don't need to handle that case yet. But there's a way of just adding in a struct that kind of looks like this. Basically like that, where you would have an input ID that is the first input, and then you would have a list of inputs, but we don't need this yet, so I'm not going to implement that just for simplicity's sake. And then this is basically what we could have, but we have the STB library here, so then this can be a dynamic array. So we don't need these because that's included. And the program won't contain this. This will actually be the function that contains this, but we're not there yet. Currently, this is all of our program, so we don't need to worry about that. So I think this is the bare minimum of what we would need to implement an IR. So the instruction ID refers to the index in this array right here. Yeah, so I think then we would need some helper functions for this, I guess. Wonder if we should call this IR, because we call the other one AST, so this should be IR, right? Let's do that. I learned a neat trick. You can do this, and this zeroes out the whole structure, which is handy. I might switch to doing this instead of using memset everywhere, because this is just more succinct and less error prone. Now we have the AST node here, so I wonder if we want to keep a reference to the AST. That would make sense. Oh, I'm putting my types the other way around. I'm so used to Go. Okay. I'm surprised I don't make that mistake more often. And actually we can just go, and this will actually zero out the rest of the structure, which is handy. That's basically what we want. But we got to use the STB functions. Let me just look those up. Is it insert, put, array put. I'm going to put it in. Now I'm trying to decide how to handle adding the operands onto here, because some things require operands, some things don't. I guess as a separate function is probably best. Or I guess, yeah, there could be different functions for each one. Add inster. Yeah, I'm going to just have separate functions for each one. So yeah, I'm going to kind of make it so that you can do this. So then you can kind of just chain which setter you need for the operands onto adding the instruction, and then it'll return the instruction ID, kind of like a pass through. So I think this will be a good API to use. Oh, it's saying assert is not. I guess I have to include it. Okay, so these are the functions for setting the inputs of the 3 different types. I'm using assert here just to make sure that it's used correctly. This kind of just finds bugs a little bit earlier. And there's a way to compile without the asserts if you want to go a little bit faster. Yeah, so I think that's good for adding instructions. So I think this is all we need for now. I'm debating whether or not to add a way to traverse the IR right now. I don't think we're going to get as far as using it this episode, so I think I'm going to move on to generating the IR from... Well, actually, I just had a thought. We need to be able to test this somehow. So we do need something... Yeah, so I guess pretty printing. You've seen me do pretty printing before, so I think I'm just gonna hammer that out. Yeah. So I think that's basically it. So we just have a method, a function to print an individual instruction. And I'm going to use this format where the instruction is assigned to a temporary variable each time. These ones are missing that. And the error opcode doesn't return anything. This one might be handy. So if a instruction produces a result, it'll be assigned to a variable, and then we print the variables that are the inputs there. We could actually simplify this a bit, I think. Instead of going by the op name itself, we could just go by the input type. Let's do that instead. Okay, so I just refactored this to select the number of, or to switch off of the number of inputs. Since we're putting the op name in there anyway, that makes a lot more sense. So I think this is good. What's this saying? And then when we dump, we can just iterate over all of the instructions, and that I think will do. So we can kind of write a test now. Okay, we've got passing tests here. So I'm just doing a manual creation of the IR for now, and then just printing it out to a buffer, doing a dump, and then asserting the string is equal to what is expected here. And that seems to work. So we have IR being generated that looks like this. So now we just need to convert the AST into this format. So I think that's going to be a little bit easier if we build a struct for that. Okay, so I've got an add inster method that's just taking the AST node, and in the case of a literal, it's doing this code here. It finds the token in the AST. It creates an instruction for it that's an op int. It converts the token string into an unsigned long, which is an uint64t. One issue that might arise is that this method here can't take account of characters. I'm not sure if there is a method that does take, like a function, sorry, that does take the account of characters. I looked up in the man page, which you might have seen, to try and discover if the end pointer would be a stopping point, but it doesn't seem to be. So I'm not quite sure if there's a different variation of this function that takes a number of characters. Yeah, it doesn't really matter. It'll stop once it hits the white space underneath after the token anyway. So it's not that big of a deal, but it would be nicer if I could give it a character count. Anyway, then you set the instructions value here, and then we're putting it on a stack. And I'll get to why we need a stack in just a moment, but essentially we are building SSA, which is static single assignment. So in here, you'll see that each variable is only assigned once. And so we need to keep track of what the variables are, i.e. these variables here. And we're doing that just with a stack. So I think that's everything for literals. Let's implement the other operations. So apparently I forgot to put this into the header file, so then we can use it elsewhere. So I'm just going to do that now. Yeah, so I'm not sure if I actually need a stack, because the the child nodes will be right here. So we're actually just using the call stack as the stack. So I don't think we actually need a stack. So I'm just going to remove the stack for now because I don't think we'll need it yet. We might in the future. Then we don't need this. Okay, I think this is how binary can be implemented. We just take a child iterator. We know there's two children, so we just iterate over it twice, once for the left and once for the right. We convert those into instructions, and we're just using the call stack as a stack in this case, and we're just recursing over it. I think this should work. I'm not totally sold on using a switch statement here. This would probably be better as a lookup table, which I suppose we could switch to. Yeah, let's just switch this to a lookup table. There we go. We've got a just a lookup table. Now, if a type that's not in the lookup table but is larger than this is found, then it'll read past the end of this array, which is not great. Let's just add a fix me on here. So that'll just remind me to come back and fix this later. Probably the easiest fix would be to have like a tk num types or something like that, and then just put like tk num types, something like that, and then it'll ensure that this is the same length as the token types enum, but I'll revisit that later. It shouldn't happen in production code. It's just during development it can happen, and that could lead to very strange behavior because it'll read whatever's after this, and that can be super confusing if that happens. So it's not very defensive to do it this way. I'm not going to worry about it right now, but this fix me here is to remind me later to come back and fix that, because I guarantee you I'm going to get hit by this, and then I'll see the fix me, and then I'll be like, oh, I should probably fix that now. So yeah. Okay, so we've got binary nodes done. Oh, and by the way, this is why I wanted the binary to have the token in it, because then the only thing that's different between all of the binary types is just this line right here. And that can be easily a lookup table. So yeah, it just means I don't have to duplicate this code for a bunch of different node types. I think that's it. Yeah, so there isn't a node for the program as a whole. I wonder if we should add that. I think we can add that later. I'm just going to go with yeah, there isn't really a node for the result. And that should be like a return statement or something like that. But for now, I'll just go invalid node or node. So we're just using a root builder method to build the IR. And in this, we'll just use no node as the AST node. But if we have an AST node for a return statement or the program or something like that, then we could refer to it in here instead of no node. And then this is the part that returns the error level. So I think that's good. Let's modify this test to actually parse and actually we could probably convert this into a table test now. All right, we have passing tests. This one was kind of a surprise because the order that it emits the instructions is different than I was expecting it to. Could probably optimize that, maybe. Trying to think how you would do that. Yeah, I don't know how you would do that other than like some sort of instruction scheduling or something like that. I'm not going to worry too much about that. I mean, potentially the idea of using a stack might fix this. The issue that I'm seeing is that we don't need V2 until, or no, we don't need V0 until right before V4. And yeah, just converting this into code is going to be annoying because, yeah. Oh well. Anyway, we'll pass that hurdle later, I think. So yeah, we do have passing test cases. So we've got the IR being built for all of these. It is in static single assignment notation, but we don't have any branches in the control flow, so we're not getting into the complicated bits yet of doing fee instructions and things like that. That will come eventually. Yeah, I'm just trying to decide what to do next, whether we continue with this and try and generate code from it. Generating code requires probably doing some transformations to the IR because this is in the wrong order to make it easy. V3 here should be on the left-hand side where V0 is, so that the result can be passed straight through. So yeah, this is not the best. Is it correct though? V1, 5 minus 7. Yeah, it's correct. No, we could probably do this. We just need a crude register allocator. But I think that's better for the next video. So I think in the next video, we'll figure out how to allocate registers and produce the code for this. So yeah, I think, yeah, next episode we'll handle generating code. So before we wrap this up, I think it would be good to do a little bit of cleanup here and move things to where they should be rather than in the test file. So let's do that. Okay, so it's all refactored. I moved it into here. There was an error with this here. I don't know how unportable this is, so I'm just going to leave it as is. That should work fine. All of the tests still pass. So, yeah, so I think this is a good place to call it quits for this episode. So in this episode, we built an intermediate representation that allows us to build an SSA form from the abstract syntax tree. And then we got test cases working with the pretty printed form of the intermediate representation. And this is looking a lot more like machine code. So in theory, we just assign registers to these things and the program should work. And it can be a later optimization to try and reuse registers as much as possible. But for now, we can get ourselves unblocked by doing that. But that will be in the next episode probably. So yeah. Thank you very much for watching, and thank you for supporting this channel if you do. It's very much appreciated. So have yourself a great day. Bye.